Recording's rolling. Thursday, December 4th. Right, so I'm doing this video for all my classes. So I gotta get some context here because the fast, all my classes are out of alignment by a day for a while. So in period one, we're doing midterm review, part three, same set of guide questions we've been in the last couple of days. And then I need to do some energy and momentum review with you guys. So I'm thinking tomorrow I'll do energy review and then momentum was on Monday. And then I'll get you guys that in-class quiz on energy and momentum on Tuesday. And this will be a little bit easier than the normal take-home quiz I give you guys. All right, my afternoon classes, I will start the energy review today, and then we're going to do science articles tomorrow. I think it's a pretty good activity worth the time to, right? And then everybody will be back in alignment. All right, so then yeah, and then next week, Wednesday, Thursday, Friday, give you guys some review puzzles, and we'll do quiz makeups and all that. All right, so you guys good with the agenda? What's going on? All right, there is one question that showed up last day or two that I do want to readdress. Actually, I forget which class came up. For you guys in front of you, it might come up today. Okay. But do you guys remember this? This is familiar? Okay. So what's the gravity field relative to say a planet? Okay. So guys, if you're right at the center, what's the gravity field right at the center?
Zero.
Yeah, it'd be zero. Right? Because every grain of sand on Earth pulls you a different way. It all cancels out. You wouldn't be floating around like an astronaut if there was like a little cave right in the middle. Okay. On the surface, of course, we experience 9.8 meters per second squared. Right? That's locked in at the surface right here. And as you fly off in a rocket, doesn't gravity field dissipate one over the distance squared? Is that all true? All right. All right. Now, if the planet did have uniform density, right, no, that's a huge simplification, but if that was true, if it was uniformly dense all the way through, you can show that there is a direct relationship between the gravity field and your distance from the center. Say if you're like to tunnel down for the center, get that. Okay. If you look at your notes from probably a couple months back or so, we worked this out in class. It calls like a square cube law, or there's like a whole math process behind this. But that's again only with this assumption of uniform density. I did look this up, and if guys, do you guys think the density there increases as you go down right, into the core? It gets more and more dense, right? So I did look this up, and this is more accurately what it actually looks like. Right, so what's gravity field is a function of radius from the center, right? So this line right here points to okay, if it had been constant density, just like my poster shows to, right? But realistically, with these different layers of Earth, as it gets dense, the deeper you go, right? It actually looks more like this, right? So one of the questions on your study guide says, "Where do you weigh the most relative to Earth?" Right? And the answer I had you guys choose was basically on the surface, right? I'm going to throw that question out. That question's not going to show up in the midterm because, well, it's not exactly like scientifically accurate. Okay, you guys see that? All right. So a little clarification there.